Okay, good morning, good afternoon, everyone, and welcome to Biomass Canada Cluster Project Updates webinar series. My name is Mahmoud Ebadian. I'm a research associate at Biomass and Bioenergy Research Group at the University of British Columbia, working on biomass logistics and supply chain. And as you may know that we started this webinar series last week, we had updates from two projects as part of the Biomass Canada cluster. And today we will have updates from two other projects, and I'm going to introduce the presenter in a few minutes. But before that, I just want to let you know that if you are interested in the previous webinars, especially the last week slide and also recording, you can find them on the webinar page on the Biomass Canada website. And also, I want to give you a quick overview of Biomass Canada cluster, just in case you are not familiar with the cluster. So the cluster was established in 2018 and led by Biofuel Canada Network with the financial support from Agriculture and Agri-Food Canada's Agri-Science Program, and also the contribution from the industrial partners. And the focus of the cluster for now is on agriculture biomass and increasing and trying to promote the use of agriculture biomass for bioenergy, biofuels, and other bio-based products. And for now, we have 10 activities or projects as part of the Biomass Canada cluster. And the focus is on producing biomass, pre-processing, and improving the quality biomass. And also part of the focus is on distribution and logistics and supply chain. So again, the goal is to how we can improve the production, pre-processing, and also logistics of biomass, so we can actually make it available as a low-cost, low-carbon intensity feedstock for bioenergy, biofuels, and other bio-based products. And so, as I mentioned, that for each webinar, we have two activities. For today, we have activity number 2 and 3. Activity 2 is led by Dr. Lope Tabil, a professor of biological engineering at the Department of Chemical and Biological Engineering at the University of Saskatchewan. And he's going to give an update on the pre-treatment and pre-processing of biomass feedstock for bioenergy and bioproducts. And he has actually 5 of his graduate students, the PhD students that have been working on this project. So each of them, they are going to briefly also provide the update on the research they have been doing in the last 3 years. And the second presentation is about the update on activity number 3, which is led by Dr. Charles Shu. He's a professor at the Department of Chemical and Biochemical Engineering at the Western University. And he will be giving updates on zero waste process for conversion of wet greenhouse waste and agroforestry residue into recycled water, bioenergy, and also high-value bioproducts. And also one of his postdocs, she's also giving updates on the research she has been doing on activity 3. So before I give it to Lope to a such presentation, again, quickly, just let you know that this webinar is being recorded, and a copy of the slide and also recording will be available on Biomass Canada website. And also, I encourage everyone to put your question in the Q&A box, not the chat box. So that's going to make the job easier for me to find a question. And after the presentation, we can have a Q&A session to address your question. So with that, I give the floor to Lope, and we look forward to your presentation, Lope.
Okay. I'm just sharing my screen now.
Yep, sounds good.
Can you see the full screen now?
Not yet.
Okay, good.
Yeah, no, sounds good. Thank you.
Thank you very much. Our presentation this morning is going to be on pre-treatment and pre-processing of biomass feedstock for bioenergy and bioproducts. This is with respect to activity 2, which is biomass feedstock for food and energy security in the North, solutions to technical issues, economic feasibility, and environmental sustainability. At the outset, I would like to acknowledge my co-authors and co-presenters, Kong Dao, Ono Ologo, Obiora Ago, Chukwuka Onyenwoki, as well as Payman Alisali. Also, we have our co-authors, Duncan Cree of College of Engineering, University of Saskatchewan, Tim Damonsu and Edmond Mupondwa of Saskatoon Research Center of Agriculture and Agri-Food, Canada. So I would like to acknowledge the Government of Canada for funding this research through the Canadian Agricultural Partnership and also the biomass cluster holder, which is BiofuelNet Canada. Our partners are Middle Lake Tribal Council Industrial Investment, Richardson Milling, that is an oat processor here in Saskatchewan. Of course, the provincial utility firm, SAS Power, Floating Gardens, Mystic Management, as well as University of Saskatchewan and Agriculture and Agri-Food Canada. So the goals of this project are to support agricultural growers in northern latitudes, particularly in northern Saskatchewan, through the supply of locally produced or locally sourced biomass feedstock for combined heat and power generation, and to improve the market opportunities for this biomass for conversion to bioenergy and bioproducts, and develop environmentally sustainable technologies and bioproducts for the bioeconomy, and contribute to lowering greenhouse gas emissions. Now, the specific objectives of the activity that is covered in this presentation are the following. We want to investigate how various processing and pre-treatment options influence the physical and physical properties and chemical composition of biomass, and determine how pre-treatments such as biomass densification and the like affect or and subsequent conversion to bioproducts and bioenergy. Now, the technical accomplishments of this project is related to the mentioned objectives, and so we have five updates here. One is on modeling of fungal growth on lignocellulosic substrate. Another one is fungal and ultrasonic pretreatment of switchgrass, microwave-assisted torrefaction of sawdust and oat straw. Another one is impact of microwave absorber in torrefaction of camelina straw and switchgrass for biofuel pellets production, and torrefaction and densification of sawdust. And so I'll give to you Kong Dao for his portion of the study.
Hello, everyone. My name is Kung Dao. Today, I would like to present part of my second objective during my PhD work. In this study, the growth of phanerochaete chrysosporium on camelina straw was mathematically modeled to explore the interaction between microbial growth, substrate consumption, gas exchange, and enzyme production. The data will be used for my third objective of life cycle assessment of the fuel production using the microbial pretreatment process. Next slide, please. First 3 grams of fine substrate were incubated with 2 ml of inoculum liquid inside a 250 ml Erlenmeyer flask for 5 weeks. Every 2 days, the Hespe gas of the flask were collected to analyze the concentration of oxygen and carbon dioxide, and the Hespe was flushed to bring back the 100% oxygen environment after its collection. The substrate was collected to analyze its carbohydrate and lignin content, as well as the dry matter loss. The fungal biomass content and enzyme production were determined by total chiral nitrogen content and ergosterone content. Next slide, please. So 5 mathematical models were proposed to fit the experimental data. The logistic model was used for fungal biomass growth, incorporating the lag phase, the exponential growth, and the stationary phase of the growth. M is the maximum specific growth rate, and XM and XO is the maximum and initial fungal biomass content. The oxygen uptake rates were linearly correlated with fungal growth with 2 more parameters, including YXO, the yield coefficient of the substrate to fungal biomass growth, and the MO, the maintenance coefficient. The model of hollow cellulose substrate consumption includes the substrate consumed for fungal growth, the maintenance of fungal biomass, and the lignin degradation, assuming only cellulose and hemicellulose were the sources of carbon and energy during solid-state fermentation. The enzyme production model was described by Ludeking and Paret equation, with alpha and beta were growth and non-growth constant for enzyme production. And the lignin degradation model was assumed as a non-growth reaction, with the degradation coefficient KL being described as an exponential function of decay time, with K1 and K2 being the 2 lignin degradation coefficient. Next slide, please. So the models were proven to fit the experimental data quite well, with the coefficient of determination of more than 90%, except in the case of enzyme production. The fungal growth model showed the lag phase during the first week and exponentially increased between 7 to 20 days and maximize after 3 weeks. The maximum specific growth rate was 0.5 per day, and the maximum fungal biomass concentration was 0.006 gram biomass per gram dry matter substrate. In the oxygen uptake model, the coefficient of oxygen to fungal biomass, YXO, was estimated at around 0.004 gram per millimole, and the maintenance coefficient MO was around 21.6 millimole per gram per day. In the substrate consumption model, the yield coefficient of the substrate to fungal biomass was 0.6 gram biomass per gram substrate, and the lignocellulosic mass loss for maintaining fungal biomass was around 0.4 gram substrate per gram biomass per day. In the enzyme production model, the growth associated coefficient alpha was 0.09, which was much greater than 0.004 of the non-growth associated coefficient. The model poorly predicted the enzyme production with 70% R squared. It can be explained by the complexity of enzyme production during solid-state microbial pretreatment. It showed that different enzymes follow different production profile, while the activity was not necessarily correlated to the degree to which the corresponding substrate was degraded. Therefore, the empirical model was too simple to simulate the enzyme production. The lignin degradation model showed that lignin did not degrade at a constant rate. Instead, its degradation increased over time. The negative value of K2 minus 0.05 indicates that the rates of lignin degradation actually increased with time. So these are the regression models after fitting the data to the curves. Those findings will be used for my third objective related to the techno-economic analysis and life cycle assessment of the fuel production project using the microbial pretreatment. Thank you.
I'll give you here Uno. Uno, please.
Hi, everyone. Thank you for joining this webinar today. Thank you, Dr. Love, for this opportunity to present this aspect of our work. So in this aspect of our work, we investigated the impact of fungi pretreatment and its combination with ultrasonic irradiation on crop pellet production and enzymatic hydrolysis of sweetgrass. So actually, we wanted to also see the possibility of using ultrasonic irradiation as a sterilization method prior to fungal pretreatment as well as a supplementary treatment method to enhance biofuel production. Next slide. So after our experimentation, we were able to determine the optimum pre-treatment conditions. So as you can see on the slide, we selected two optimum conditions. One, based on the shortest fermentation time, and two, based on the pellet tensile strength. So from our results, we observed that the white type trimite and the B chrysophorum were better options for switchgrass pellet production. Please, next slide. So similarly, we also determine the fungi treatment conditions for enhanced enzymatic hydrolysis. In this case, we selected also two optimum conditions. So we selected of condition one based on the values of total available carbohydrates and the vinification. And then number two is based on the lowest pre-treatment severity. The next slide. So we conducted enzymatic hydrolysis of sweetgrass after subjecting it under these optimum conditions. And from the graph on the slide, we can see that the white type tramite yielded the highest total reducing sugar, which was about 65% increase compared to the untreated sweetgrass, which increased by 1% after densification. Next slide. So we also tried to produce fuel pellets using the lowest pretreatment conditions. And from the result of the physical and mechanical properties of the treated sweetgrass fuel pellet, as you can see on the slide, the properties showed lower value, which means that the quality of the pellets was not improved compared to the untreated pellets. The next slide. So we also looked at the effect of combining ultrasonic and fungi treatments on enzymatic hydrolysis of sweetgrass. So from our results, we observed that simultaneous enzymatic hydrolysis and the ultrasonification enhance enzymatic digestibility, and the results show that it gave about a threefold increase in cellulose digestion compared to the untreated sweetgrass. So from this study, we can say that ultrasonic irradiation can actually serve as an option for sterilization of substrate prior to fungi pretreatment, and as well as a supplementary pretreatment method to enhance biofuel production. So at this point, I want to stop to allow my colleague to take over from there. Thank you.
We have Walker next.
Yeah, good day all, and thank you for coming to this webinar. And especially I want to thank Dr. Lope for the opportunity given to us to present. So this aspect of the work is to investigate the effects of microwave assisted torrefaction on two selected biomass feedstock. So here we used sawdust and oat straw. So the oat straw was size reduced using the hammer mill and then stored for further use, while the sawdust was used at its ease since it does not require further size reduction. Next slide, please. So the torrefaction pretreatment was carried out at different temperature ranging from 200 to 300 degrees at a retention time of 5, 7, and 9 minutes. So we try to replicate the severity factor, which you have the mild, the medium, and the severe condition. So then after torrefaction, we went further to perform the underlisted analysis, the heating value, the microstructural analysis, ultimate analysis was further investigated to see the effect of torrefaction on the pellet form. Next slide, please. Also, the 35 samples were densified using a single pellet unit mounted on a estron. And here we try to use binders, different kind of binders. We use the torrefaction liquid and the sawdust. So we also, to determine the effect of these binders, we determine the tensile strength, the pellet tensile strength, and the moisture update of this pellet form. As you can see from this figure, E, F, G, and H are the different pellets that were formed from different binder combination. Next slide, please. So from our result, the severity factor was calculated using the equation as shown below, and the table 3 there shows that as the temperature and time increases, the severity factor increases. Table 4 shows the mass yield after torrefaction, which shows that as the severity increases, the mass yield reduces, but the liquid yield and the gas yield increases. Next slide, please. Also, we went further to see how these the size were distributed. So from the histogram shown here, the particle size was normally distributed, and this could be attributed to the fact that torrefaction pretreatment disintegrate the lignocellulose structure of biomass, thereby leading to lower shear stress and easy grindability. So this is also suitable during densification, as the smaller particle try to arrange and fill on the void space of the larger ones, thereby producing a kind of a durable, compact, and a suitable pellet. So also what the HHV, the heating value, increases as the severity also increases. Table 5 here shows also that the hemicellulose and the cellulose and lignin content were also affected, as the severity also was affected. So the next slide, please. So here we try to see the effect of binder on different pellet properties. So it can be said that the addition of torrefaction oil in pellet formulation positively influence the pellet's mechanical and thermal property. So introducing of this oil improved the surface morphology by improving the bonding mechanism of the biomass. Thus, this changes the surface by reducing the microscopic capillary, which reduce the absorption of free water. Also, from the diagram, we see the SME diagram. It shows that for closely looking at it, there is a kind of a close bonding and cementing surface compared with the non-treated biomass. So it shows that as this shows that the biodegradation of lignocellulose component of the biomass during the pretreatment release more of the binders in this material, which kind of represent the high tensile strength as seen for the most of the pellets which the bio oil, that is the torrefaction oil, was used as binders. Thank you. I leave this for the next presenter.
So we have Obiora next.
Okay, thank you for having me. I want to thank Dr. Lope for giving us the opportunity to have our work presented. I'm here to present the impact of microwave absorber in torrefaction of camelina, straws, and switchgrass for biofuel pellets production. Two dedicated energy crops were used in our study, and the camelina, which has been a breeding dedicated crop focused on agronomic and quality improvements in terms of the food and feed applications. And it has been indicated that a lot of extensive research are ongoing on the oil seed and camelina straw for industrial applications, such as in biofuel and fuel pellet development. Then on the switchgrass, there has been an extensive research as well and successful results which has been achieved in terms of the development for bioheat and bioethanol. Then as the biochar that we used is produced from forest residue, and this is used, or this was used as microwave bioabsorber. And the reason for this is to evaluate the potential use in torrefaction of camelina and switchgrass. The anticipation is to investigate the reduction in energy consumption during microwave torrefaction. Next slide, please. So the approach that we use, the microwave torrefied products are converted from low quality biomass to potential new valid products. And microwave absorber improves heat penetration, depth, and catalytic effects on the product yield and quality. So in this our study, we use two microwave torrefaction temperatures, 250 and 300 degrees centigrade, in an inert environment, and residence time 10, 15, and 20. Next slide, please. So as received camelina and biochar, including the switchgrass, the proximate analysis values, which are important for biomass energy applications. The camelina straw or switchgrass volatile matter and ash are evidence of potential high calophilic value and good heating rates. Then the switchgrass and the camelina straw showed low moisture content and bulk density compared to that of biochar. The low ash content across the samples reflects possible potential use for direct combustion or co-firing purposes. Then on the side of the figure 2, we notice kind of after the torrefaction process, after microwave torrefaction, the physical observation revealed that the volume of the solid biomass fraction reduced and became brittle and dark in color. Next slide, please. Then on our results, we looked at the two torrefaction temperatures. The A is 250 degrees centigrade and B is 300 degrees centigrade. 3 products were obtained from the microwave torrefaction process: the char residue fraction, the torrefaction liquid, which is a mixture of water, and the oil fraction, and non-condensable gas. In both samples, biochar addition increased the torrefaction temperature. Torrefaction temperatures decreased the solid yield and increased the torrefaction liquid and non-condensable gas. Next slide, please. So on this slide, we are looking at the effect of the biochar addition on the microwave torrefaction energy consumption. As anticipated, microwave absorber addition affected the heat penetration depth at torrefaction temperature in both samples. At 20% biochar addition and lower torrefaction temperature showed reduced energy consumption for torrefied camelina straw and switchgrass with biochar mixture. More analysis is still going on in our study. Thank you.
I'm going to present Payman's part of the study on torrefaction and densification of sawdust. And because we have Middle Lake Tribal Council as our partner in this activity. And so we have this study wherein we have sawdust, which we source from them, didn't need any grinding. And so we did it in a conventional torrefaction unit, which is electric heated. So if you see in the diagram or in the flow chart here, there are two wings of the flow chart, one using inside temperature to monitor torrefaction, and outside, the other one is outside temperature, is monitored for the progress of the torrefaction in the conventional unit. So they have the same flow. After biochar production, there is preconditioning with water as well as adding of additives for binding, as well as densification and production of pellets. So in this diagram or in this figure, you will see the torrefaction liquor or liquid that is being used during the process, and also the biochar used or that were produced from wood sawdust. So again, we try to optimize the temperature and the time in the torrefaction unit. Now, this table shows to us the results of the thermochemical properties of the product in that torrefied material, sawdust, have increased high heating value as well, and the increase is with respect to the severity factor of the microwave pretreatment. The elemental carbon content increased, whereas the elemental oxygen decreased as a result of torrefaction, as well as with respect to severity factor. Now you will see here a photo of the leftmost one is the non-torrefied sawdust and the corresponding pellets that are being used. To the other end of the photo is the torrefied, high severity factor product of sawdust, and in which we added steam treated sawdust. So in this particular study, the sawdust was also steam exploded, and a portion of it was 20% was added as binder in the process. And so we definitely have good pellets produced in this with the addition of binders. In this slide here, table 2 shows to us the mechanical strength has been enhanced by adding of 20%, because we know that with torrefaction, there's gonna be less binding of torrefied particles. So we added steam exploded sawdust for this, and so adding 20% of the steam treated sawdust can improve our torrefied sawdust by pellets. Now let me summarize what we have in our presentation this morning. The mathematical models used to describe solid state, the SSF of camelina straw, and by P. chrysosporium sufficiently illustrate accurate predictions for fungal growth, oxygen uptake, holocellulose consumption, enzyme production, and the like. Now, these models will be useful in the design, in the scale up of the operation, and of course, these are useful also in our techno-economic analysis of such a undertaking for a fungal growth of biomass, a fungal pre-treatment of biomass. In the other study on the fungal and electronic ultrasonic pretreatment of switchgrass and low severity fungal pretreatment favor enzymatic hydrolysis, whereas high severity improve tensile strength of the fuel pellets that were produced. And although ultrasonic irradiation serve as sterilization option, in solid state fermentation of biomass, it did not enhance enzymatic digestibility compared to SSF with autoclave as a sterilization method. In the next study on the microwave torrefaction of sawdust and oat straw, we can summarize that the addition of torrefaction liquid sort of use the byproduct of torrefaction can positively or has positively influenced the mechanical and thermal properties of your biofuel pellets. And the torrefaction liquid improve also the surface morphology of the cut pellets, showing that the particles were bound together very well. And on the impact of microwave absorber study, it can be summarized that the addition of biochar allowed unifying biomass heating, playing a catalytic role as anticipated in the heating process. And the study observed that using a microwave absorber can reduce the torrefaction process and increase the quality of value-added products obtained from camelina straw and switchgrass. And to summarize, for the torrefaction and densification of sawdust study, we say that in this case wherein we use a binder made of steam exploded or treated spruce sawdust, it acted positively on the binding of particles for our fuel pellets, and the chemical recovery of torrefaction liquor can have uses elsewhere. It can be used for a number of products, and of course, in one of our studies, it was used to be a binder for fuel pellets. So let me just say the relevance of these studies that we tried to utilize byproducts of crop production and forest harvest and turned into potentially into energy and heat. And of course, we help to improve air quality by avoiding use, for example, of TP burners, that the one that we encountered with our partner to dispose of residues, for example, and facilitate in the shift from coal-fired to biomass-fired plants for producing heat and energy. And developing pretreatment technologies that can be scaled and back up with data. So the future work will be on a wrap-up of data analysis about pretreatment experiments and continue with our techno-economic analysis and life cycle assessment for this particular project. And with that, thank you for listening to our presentation, and thanks to our graduate students who were on time.
Okay, thank you very much, Lope, and also John, Ono, Chukwuka, and Obiora for joining and also giving update about the research you have been doing. And of course, we know that especially for agriculture biomass, because of the low quality we have, pre-treatment is very critical, and Lope has been working in this area for a long time, and we have lots of knowledge that his research group has been developing on the pre-treatment of different types of biomass. We have about 10 minutes for a Q&A. I'm going to ask you the first question, Lope. You mentioned, if I'm not mistaken, you said the binder was steam-treated spruce sawdust, right?
Yes.
And then you applied to the sawdust, or you applied that to agriculture biomass in the process?
We applied it to the torrefied sawdust. So because we have two parts of the study. We have a torrefied sawdust. We have also steam-treated sawdust. And so what we did was, in the other study, we took some steam-treated torrefied sawdust, which produced good quality pellets.
Oh, okay. And also you said that the torrefaction liquid, again, you recycle back into the pre-treatment process. Okay, it's not like that was like a bioproduct.
Yes,
right?
Although there are gonna be potential uses of it, but we have, for a ready use would be to recycle it and use it as an additive during pellet production, so that your pellets will be in good shape.
So you applied at the pelletization process, like sprayed on the biomass, right? Is it? Okay. Yeah. And I have one more question. So you mentioned that I get Chukwuka mentioned that he's been using camelina straw. So I'm just curious, because this is a new crop in Canada, what is the yield of camelina straw, like per hectare or per acre? Do you have any data on that?
Sorry, it was Obiora that mentioned that.
It's me that mentioned camelina.
Oh, okay, sorry. Yeah, Obiora. So do you know any, like, how much, like, how many tons you can get per acres or per hectares?
At the moment, I think it's over 1.6 million tons per year. That was the data of 2018.
Okay.
You know, currently, Canada is just this is a new type of dedicated crop. So it has been researched in the US, because US has been using that to develop something on biofuel jet.
Okay.
So it's a new dedicated
but we
crop.
have a Canadian company in Saskatchewan, right?
Yes, that is working on that now. Yes.
Oh, okay. And how is it different from canola straw? Do you see a big difference? Like canola straw, because both of them are oilseed crops. So do you see a big difference between camelina straw and also canola straw in terms of the properties?
Yes, like I said at the end of my presentation, we are still working on that. So
Okay.
I think there will be, because on the seed seed itself, so there is a little bit I would say good yield in terms of the byproduct by the camelina oil. So on the part of the straw, there is kind of limited literature on that. So I believe after my work, I can look at other literatures and see how to make the comparison, and that question will be answered.
Okay, great. Thank you. Thanks. Again, thank you a lot, Lope and
There's a question of Shahab.
Pardon me?
There's a question by Shahab on Q&A.
Oh, yes, sorry, I missed that one. So yeah, like how do you do the tensile strengths? Yeah, go ahead, Lope.
Right. Pellet tensile strength we use, but the process actually in testing is compression test, except that we prepare the sample into thin strips around 2 to 3 millimeters and then compress them. As a result of that, the particle or the specimen will break up by tension, and so that's why we indicate the process as, or the value as tensile strength. I see this as a more reliable indicator in the absence of durability, because it gives the capability of the material to at what is the tensile strength, what level of strength is it there in order for it to disintegrate. Whereas a lot of people I have seen in literature, they just compress the pellets very well right away. To me, that kind of test is not really reliable, not comparable with the durability test.
Thank you, Lope. Okay, I guess we can move on to the next presentation. Again, thanks, Lope, and graduate students to join and also present. We really appreciate that. And for the next presentation, we have Charles and his postdoc that they are going to give update on activity number 3. Over to you, Charles.
Okay, thank you. Yeah, thank you, Mahmoud. So can you see my screen first?
Yes, sounds good. Thank you.
Okay, well, good. So first of all, I enjoy the presentation by Lopez and his group. So it's a very interesting research already done on the pelletization and then the bioenergy application, as well as some of the bio-based product research, which is also interesting to me. So my activities are a little bit different from the bioenergy. So we're looking at more on the bio-based product, particularly focus on the utilize the greenhouse waste and the agricultural residue to produce some of the bio-based polymer.
And then some of bio-based polymer can be used back for greenhouse and agriculture application. So it's kind of focused more on the circular economy to reduce the waste generation and then produce more value, added value from the bio waste. So today, actually, so I'm going to present this together with my postdoc fellow, Dr. Lee, Hongwei Lee, and she is already in the room. And also, I want to acknowledge my funding. So from the BiofuelNet or from Biomass Canada, Agriculture Agri-Food Canada, and my partners, so Western Maple Bioresources, and the other companies, including here Mutual Farm and also the Emira own greenhouse farm. And my research partner in AFC is Dr. Zhe Chunyuan. So unfortunately, he's not able to join us today. So I'm going to present the work for him, for a part of work for him. So the goal or the research objective for this research is the valorization of biomass, particularly greenhouse, particular wet greenhouse waste, and some other. I just want to put my laser here. Yeah. So and also crop residue and forestry residue for recycling the water and bioenergy, particularly more focus on high value byproduct, to reduce the greenhouse gas emission and also strengthen the bioeconomy and sustainability for Canadian agriculture and agri-food sectors. So the project or the objective is the more specific is develop innovative zero waste technology to convert those greenhouse waste and agricultural residue to bio-based product. So particularly focus on more the some example I listed here is bio-based hydroponic foam for seeding, germination, and then plant cultivation. Bio-based formaldehyde-free wood adhesive for the furniture industry, and bio-based super-absorbent polymer for agricultural soil water retention purpose. And then recycle water and bioenergy. So this is my focus in the in academia side, and the vote one, which is agriculture agri-food side. So Dr. Yuan, so his part is more focused on to demonstrate the application for bio-based hydroponic foam, and then the bio-based sap, the super absorbent polymer in greenhouse, and their degradability for those materials in nature. So this is the overall diagram show the approach what we have taken in this project. So basically, we take the feedstock from greenhouse waste, agricultural waste residue, and the forestry residue. We do fractionation. We can get the lignin and cellulose, and the lignin will be produced. Will be used for produce a bio-based formaldehyde-free wood adhesives. And the cellulose, we're going to convert that to bio-based super absorbent polymer. And also another product recently we developed from this cellulose is the concrete water reducer. So those are the bio-based product from the lignin and cellulose. And then the greenhouse waste, we go for thermochemical conversion. So hydrothermal liquefaction. We produce the biochar and we produce recycled water for greenhouse as a heat, as bioenergy. And then the bio-oil, or we call it biopolyols, will be converted to, already has been converted to bio-based hydroponic form, and then used to do the seeding, germination, and also growth media in the greenhouse. So this is circular. So the technical comprehension so far and the progress we made so far, we have several deliverables. So the first deliverables will really demonstrate that cost-effective, scalable hydrothermal liquefaction process for conversion of wet greenhouse waste into biochar recycled water. So this deliverables has been completed 100%. So we already developed the environmental friendly process to convert those to biopolyol and recycled water. And we obtained the scale 1.5 kilogram per hour in the lab scale, but it's relatively larger than bench scale. And then we accomplished a 35% bio or biopolyol yield, and then 85% biomass conversion. And we complete the hydrothermal liquefaction, agriculture, and forestry residue in the scale in a batch 5 kilogram per batch scale. And this is already accomplished in the project. For developer 2 is to the bio produced from the hydrothermal liquefaction. The process, we substitute up to 100% petroleum-based biopolyols to make a bio-based the polyurethane form. So in this project, we are already in progress up to 80% completion. So my postdoc fellow, Dr. Lee, is going to talk this more because this is our focus in the past year. So develop the bio-based polyol and then convert it to bio-based polyurethane hydroponic form. For developer 3 is to crop residue utilization to go through the fractionation. And we produce the lignin for the formaldehyde-free wood adhesives. And then the cellulose, we go for the utilization for, as I said before, is a bio-based super absorbent polymer. And for wood adhesives, we already tested that in the past year. So for different type of wood product, for the OSB, for plywood, and for particle board, fiber board. So this has been finished up about 90% complete. The developer 4 is about how to convert the cellulose, particularly the cellulose fractionated from crop residue, to make a bio-based super absorbent polymer. And this will be used for soil water retention purpose. And this project has been finished by about 80% by far. Final deliverable is done mainly by our colleagues in Agriculture Agri-Food Canada. So Dr. Yuan's team and partner with me and also another colleague in Lakehead University. So we have demonstrated that biodegradability for those bio-based polymer, particularly in this only bio-based polyurethane form, biodegradation. So we have done the research and also published one paper recently. So this biodegradation study we already complete. So from this slide and on, I'm going to ask Dr. Lee to continue the presentation and to focus more on the conversion agriculture and the greenhouse waste to bio-based hydroponic form. So Dr. Lee, so it's time for you to present. So you just tell me which slide I'm going to, just run the slide for you.
Sure. Firstly, good afternoon, everyone. I'm so happy to be here with my supervisor, Dr. Shu, to present our research work. So for my part, I would like to update our research activities on conversion of agriculture and greenhouse wastes into bio-based hydroponic forms. So greenhouse wastes, including the leaves, stems, and vines of greenhouse plants, are abundant renewable resources with more than 2 million hectares of greenhouses all over the world. Greenhouse wastes are usually disposed by landfill or simply by dumping them in dry ravines or open spaces, leading to uncontrolled burning, blockage of riverbeds, poisoning of cattle and sheep, and causing a visual blight on the landscape. Next, please. Or PU is popular as packing, insulation, bedding, and cushion materials. And the global PU foam market was projected to grow from $37.8 billion US in 2020 at a CAGR of 7.5% to 54.3 billion US dollars by 2025. Next, please. As we all know, conventional PU foam is heavily fossil dependent because the two major components, polyols and isocyanates, they are both derived from fossil resources. As reported by Research and Market, the market for BPU foam, that is a bio-based polyurethane foam, was around 27 kilotons in 2020, and it is expected to grow at a CAGR of more than 3.5% in terms of the volume to 2026. Next, please. And hydroponic PU foams, they are the top 17 best growing media for soilless cultivation. Besides, hydrothermal liquefaction or simply liquefaction has been applied as a cost-effective conversion technology to convert biomass into liquid products. We also call it biocrude oil or biopolyols that can be used directly for synthesis of bio-based polymer materials. Next, please. So our motivation is that if liquefied greenhouse wastes were used for the preparation of bio-based PU or BPU foams, particularly hydroponic PU foams for soilless cultivation, it would significantly boost cyclic economics of greenhouse wastes, increasing the added value of greenhouse wastes and lowering disposal costs. And our approaches are that greenhouses wastes are mainly composed of three major components: cellulose, hemicellulose, and lignin, all of them containing hydroxyl groups in their structures. Through liquefaction treatment, the three major components are decomposed or depolymerized into oligomers. We also call it bio-oils, with active hydroxyl groups, which were used as alternative to petroleum-based polyol for the preparation of BPU foams. Next, please. Our methodologies include bio-oil production, hydroponic PU foam preparation, and greenhouse tests. Next, please. So for the bio-oil production, we introduced agricultural and greenhouse wastes into our 16-liter reactor, and specific conditions. After filtration and rotary evaporation procedures, we obtained our bio-oil products. Next, please. So for the liquefaction conditions, we firstly investigated the effects of temperature on the yield of bio-oil. As we can see from the figure, even though the best temperature for liquefaction or cornstalk or greenhouse wastes or their mixtures was 290 centigrade in terms of the highest oil yield. 270 centigrade was determined taking energy cost into account. Next, please. Besides, the effects of residence time, water ethanol ratio, as well as the amount of catalyst on the yield of bio-oil was also simply investigated. And finally, we found the optimal conditions are 20% biomass, 10% ethanol, 70% water, with 15% sodium hydroxide as a catalyst for 1.5 hours at 270 centigrade. Next, please. Table 1 presents the properties of bio-oil from cornstalk and greenhouse waste liquefaction. As we can see, the oil yield achieved was around 56%. The hydroxyl number of our bio-oil was around 530 milligram potassium hydroxide per gram, and the molecular weight of the bio-oil was around 1,000 gram per mole. Next, please. And then we moved to the preparation of hydroponic BPU foams. As shown in this diagram, firstly, we introduced bio-oil, catalysts, blowing agent into the foaming cup, following by the stirring and 3000 RPM for 60 seconds, and then PMDI is added into the mixture, following by another 30-second stirring and 3000 RPM. Finally, the mixture is left in the film hood to foaming and curing freely. And then we got our BPU foam samples. Next, please. This table gives the physical properties of BPU foam samples from some of our experimental trials, and we found the foam number 11 an optimal foam. Next, please. As shown in table 2, most of the prepared BPU foam samples had densities in the range of 30 to 170 kilograms per cubic meter, indicating the variability of planting. And then the optimal foam recipe resulted a foam with around 90% open cell content, which is essential for oxygen infiltration. Finally, the optimal foam has a high water absorption capacity, suggesting it can absorb enough water for plant growing. Next, please. Besides, biodegradability experiments were also conducted for BPU foams prepared with various bio-oil content. Figure 1 shows the BPU foams degradation by selected bacteria for 8 weeks. Next, please. Figure 2 shows the influence of incubation time on weight loss of bio-based PU hydroponic foam samples. As we can see from the figure, all BPU foam samples prepared with greenhouse waste and agriculture residues exhibited better biodegradability than reference foam prepared with petroleum polyol. Next, please. And figure 3 presents the FKR spectra of the reference and 50% BPU foam samples before and after inoculation with the bacteria for 8 weeks. As we can see, the decrease in intensity of peaks were observed, which were likely caused by the hydrolysis of ester, ether, and urethane bonds in the foam structure and loss of other unstable functional groups. Next, please. From our TGA analysis, comparing with those at week 0, all BPU foam at week 8 are relatively less thermally stable and started to degrade at a very low temperature. Next, please. Figure 6 shows the SEM macrographs of BPU foams after degradation by bacteria for 8 weeks. As we can see from the figure, 50% BPU foam exhibited the strongest biofilm forming capacity of bacteria on its exterior surface. Next, please. Last but not least, we've also conducted seed germination test by using tomato seeds. As we can see, we had 3 types of planting samples: rock wool, which is a commercial germination material; petroleum-based PU foams, which were prepared by ourselves; BPU foams, which were derived from agriculture and greenhouse wastes. Next, please. From our results, the commercial foam had both germination and emergence rate as high as 87%, while PU foam only showed 30% and 27% respectively. And the BPU foam had the lowest percentage of both rates. The reasons for germination test failure include, firstly, BPU foam properties. Our BPU foams had a very long water absorption time, more than 10 minutes to get a full wetness of a foam body. Secondly, it's caused by the error. due to the high vaporization of water at high temperature in the greenhouse, it did not keep the seed moist, resulting in the seed being killed after breaking dormancy. Secondly, it's caused by the system error. Next, please. At the same time, we conducted plant growing test at Shouguang Company in China. This picture shows the state of the plant at day 1. Next, please. After 1 month, as we can see, the root of the plants did not develop successfully. Based on the results of both germination and planting tests, our directions to improve include improve the open cell content, to decrease foam mechanical properties, and to increase bio-oil content. Next, please. This table shows the physical properties of our BPU foam samples from our modified recipes. Among these recipes, we can see the foam number 15, an optimal foam sample with a short water absorption time. Next, please. As we can see from the table, water absorption time can be as short as 8 seconds, indicating the foam body's rapid wetness upon contact with water. And even though the foam density increased, it's still within the range of 20 to 200 kilograms per cubic meter for soilless growing media. The optimal foam sample had an open cell content around 70%, which was 10% higher than the requirement for soilless growing media. Next, please. And table 4 gives us the mechanical properties of a commercial and BPU foam samples. As shown in this table, our BPU foam samples had a comparable mechanical properties with the commercial hydroponic media. Next, please. And then we conducted self-germination test at this time by using the optimal foam samples. The most improvement at this is that the foam body can get fully wet in seconds. And now, right now, we are just waiting for its germination. Next, please. Here is my summary for my research work. So firstly, efficient liquefaction conditions for agricultural and greenhouse waste were obtained. That is 20% biomass, 10% ethanol, 70% water, with 15% sodium hydroxide as an alkaline catalyst for 1.5 hours at 270 centigrade. And we achieved 56.3% of bio-oil yield with a hydroxyl number of 534 milligram potassium hydroxide per gram and a molecular weight of around 1,000 gram per mole. Secondly, biodegradation test results showed that BPU foams had a better biodegradability than the petroleum PU foams. FTIR, TGA, and SEM results indicated that the efficiency of biodegradability of BPU foam samples increased as the bio-oil content increased. And then planting experiments showed that our BPU foams derived from greenhouse and agriculture waste had the potential for application in greenhouses. Next, please. And after modification, our BPU foam can be achieved with 100% biopolyol. And the optimal BPU foam sample has the following physical properties with a density of around 86 kilograms per cubic meter, open cell content around 70%, and water absorption capacity around 530%, and the water absorption time around 12 seconds. The optimal BPU foam sample has the following mechanical properties. That is, At 10% deformation, the compression strength was 54 kPa. At 50% deformation, the compression strength was around 220 kPa. And the maximum stress was around 250 kPa. Next, please. This table gives my next step regarding my research. Specifically, by June 5th, I would conduct self-test plant germination and collect enough fresh bio oil. And by August 5th, I will prepare and send out germination samples to UWO and Shouguang Company, respectively. By the end of September 30, I hope I could get the conclusion from Shouguang Company. And by the end of this year, I would try my best to decrease foam density, making foam with a density as low as 20 kilogram per cubic meter. That's all my reports. Thanks you for listening.
Thank you, Dr. Lee, for summarizing the research update and updated on the bio-based polyurethane foam and for the hydroponic applications. Okay, so back to our activity 3 update. So here, it's some wrapping up the slides. So it's about the relevance. So this Biomass Canada cluster is focused more on advancing our emerging technology developed in our research lab. With those technology with the potential for revolutionized agricultural production of biomass and residue, and for sustainably meet Canada's growth need for biomass for fiber and fuel. So those are fit into the agri-food the program target. And the goal, we already specified that before. So simply it's valorization of biomass, particularly greenhouse waste and agricultural residue for energy, for bio-based product, and to support the Canadians' bioeconomy and sustainability, particularly in agriculture, agri-food sectors. So the critical success factors, so I present here a few of them. So first, we develop innovative zero waste technology to convert those greenhouse waste and crop residue to value-added product. And then we also patent, we want to patent 2 to 3 inventions developed from this technology for US or PCT or Canadian patents. And we also report the inventions to the university about the cellulose-based super absorbent polymer, crude cellulose-based concrete water reducer. This has already been submitted in last year. And then we training more than about 10 personnel, highly qualified piece. And some of the challenges are also summarized here. So this is about how to commercialize this technology from lab scale to larger scale. So this technical economic viability need to be further performed. So we are going to focus on that in the coming year. And then the scalability for the different process, including the produce biopolyols through hydrothermal liquefaction, and then to produce foam, produce bio-based polymer, bio-based water reducer. Those processes need to be scaled up. So the scalability would be also another challenge for this project. As for the future work, we are going to keep to do the research on scale up process for this liquefaction process, and to continuous flow reactor with 6 kilogram per hour capability in our lab. And then for deliverable 2, so we're going to demonstrate the application of a bio-based hydroponic foam for seeding, for greenhouse growth media. So this has been discussed a lot, pretty much by Dr. Lee before. And then deliverables 3 and 4. So we want to further optimize the synthesis process to produce high value byproduct, particularly the wood adhesives, and then bio-based super absorbent polymer. And finally, to perform techno-economic analysis study, so to assess the economical viability for those process and those bio-based product, the application and production. So finally, I want to thank the team. So we have this team involving Dr. Yuan, so as a research associate, and then Mrs. Flora Chow as a research technician, Dr. Lee as a postdoc fellow, and we have 4 graduate students, PhD student, Denise, Rosa, Tang, and Glenn, involved in this various part of the research. And also we involve some the technologists or some researchers from industry, from Western Maple Bioresources. So we have Alicia, Quinn, and Vincent. And from Lakehead University as an academic collaborator, Dr. Chen. And Western Maple, this Western University Biology. So we have Professor McAfee, and then we have Mrs. Wang, Aisha Wang from biology to support our research. Thank you for listening. So I would like to take some questions from you. Thank you.
Thank you very much, Charles and Hongwei. Very interesting presentation, especially Dr. Lee. What I found really interesting about your research is that you identified the areas that we can improve the biofoam, both in terms of the quality and the performance. So that I found that part very interesting, that how we know that it still is difficult to compete with petroleum-based product, but it's a very interesting progress to identify areas we need to keep working on in order to make it, at least from a quality perspective, make it compatible with petroleum-based product. So we have a couple of questions. I'm going to the first question, Charles and Hongwei, is about it's about the logistic. How do you see the logistic of collecting the greenhouse waste for hydrothermal, for HCl process, and what is the size of the reactor?
Yes, thank you, Shahab. I noticed this question from you. So the logistic, this has been discussed with our greenhouse partners. So they have lots of production of greenhouse, and the greenhouse contains lots of water. So the water content could be up to 80%. So in our research, we take that wet greenhouse waste directly. We shred them, and then we can crush them, and then we can feed the greenhouse, crush the greenhouse waste directly to our reactor. So we develop a continuous flow reactor. So it's a pipeline reactor. So the crushing and then feeding and then reaction and then final product separation could be for scale up, could be just a continuous flow. So this will be just the most ideally, so we can build a processing plant nearby, just near to the greenhouse area. So we can take greenhouse waste and then we can produce that to biopolyol and then transport the biopolyol or just make a polyurethane foam locally, just nearby the greenhouse. So this is our thinking about the logistics.
Thanks. And Lope, do you have a question?
Yes, I have a question for Hongwei. You did a number of tests on your foam samples. You have emergence tests, you have germination tests, you have also planting or growing tests. Between germination and emergence test and planting and growing test, which one do you think is a better indicator of your capability of your foam samples?
Oh, firstly, thank you, Dr. Lupi, for your questions. Yeah, and for this germination planting test, I think firstly for the maybe the germination test would be the first choice for us foam to be tested, because I saw a lot of PU polyurethane foams. They are more likely to be used as a germination test because they are very light and they can be as small as possible to be used as a germination material. And also for the next step, maybe we also can use our BPU foams as a plant growing media if our germination test get successful.
Okay, thank you.
Thank you so much.
I observed a few questions here, right? A few from Shah. So
yeah, I guess we have a couple of questions. So we go to the next one. So would degradability of the biofoam be an issue for storability of the foam?
Okay.
I can answer that quickly. Yeah, because our target to produce bio-based biodegradable foam is mainly for the greenhouse application. So we do not expect to store that foam for a long time. So we want to produce foam and then use the foam right away by greenhouse seeding and then growth. So this will not be an issue for storage. But those foam after use, we can easily degrade that and then make this foam can be easily recyclable. Not recyclable, just make a disposal much easier because it's biodegradable. So it will not impact the environment too much after use this foam in the greenhouse. So I think those biodegradability is key to how to make the foam more environmental friendly.
Okay, and just a follow-up question, Charles. So what's the situation for petroleum-based foam? So after the lifetime, so they are going to be recycled, or no, they have to actually, they send it to the landfill?
No, they have to be sent to landfill for disposal.
Oh, okay, so they are not recyclable, basically.
They're not recyclable after use.
Okay.
Waste. So we prefer to have more biodegradability. If you put a landfill, you can easily degrade that.
Okay, great. And then I guess the last question from Shab is that, have you contacted greenhouse growers in BC?
No, so far, actually, this is a very good suggestion. So Shahab, so we hope that we can build some relationship with a BC grower. So because BC have lots of the greenhouse grower there, and we can seek some potential collaboration or test there. But not only because so far we just work together with some local grower here in London area, but we can expand our collaboration with the BC greenhouse grower there.
Okay, great. And one more question is that, hopefully I pronounce it correctly because this is not my area. Will it be possible for the polyethylene, right, foam to be used in other application?
Yeah. So that's probably Dr. Lee, you can answer this because you know about polyurethane very well. What's our application for polyurethane foam? Dr. Lee,
You're muted.
Oh, I'm muted.
Sorry, I mute. Yeah, actually for the polyurethane foams, they have a wide range of applications, such as packaging, bedding, and also furniture and installation foams. But particularly for us, we are focusing on the hydroponic foams, PU foams, that can be used for our greenhouses. Actually, we also developed our installation foams, PU foams, for the buildings to use as thermal, the thermal insulation materials.
That's true. Yeah, insulation is another major application for polyurethane foam.
Okay, thank you. Edmond, do you have a question? Please go ahead.
And get my microphone back on here, Mahmoud.
Oh, sounds good. Please go ahead.
Yeah, and my camera was not working properly. Is it working now?
Yes, yeah, I can see you.
Okay, it wasn't working properly. I'm in Jurassic Park, you know. Excellent presentation, excellent work, Dr. Xu there, Charles, and you. Really work. And, you know, this is really relevant for us as, you know, we just had a transformative workshop within our department on circular economy and zero waste and getting to technologies that can help us to advance this whole area of circularity. And the work that is being done within our cluster, Biomass cluster, with you leading it there, and of course the work that was presented before there with Dr. Lopez group and all our other activities in the Biomass cluster really support this whole movement towards circularity. So it's good to see these very practical examples of how we can scale up these concepts and really get to an end product application in greenhouses. That's huge. You know, if you look at just the waste streams, and we can provide those examples. And I think we can begin to showcase this work as well as a practical demonstration, because there's an industry. Greenhouse gas waste is huge, but also the value that it adds to this sector in terms of demonstrating examples is really fantastic work. It's similar to the work that, of course, the Dr. Lopez group we are doing as well there with pre-treatment, because logistics are important as well. You got to get that balance right. And looking at the scalability of this as well, you know, that would be really some, and you are going to look at that as part of the work. We are also looking at that with Dr. Zechan Yu, as you know, the techno-economic aspects of some of this. So there's a lot of synergies in the work we are doing to look at the techno-economic aspects to scale this up. Hydrothermal liquefaction, certainly a very, very viable, clean approach to, again, advancing clean technology. So it'd be interesting really to just move in that direction. You talked about getting to 5 kilograms per hour when you're doing that scale up again, and then to be interesting to see exactly what is the size of the hydrothermal liquefaction plant, and you know how much material can we get and how close can we build it to greenhouses. So I think going forward, there's a lot of opportunity for us to work together in some of these areas to see how we can really get to a scalable concept for these wonderful technologies.
That's a very good comment. Yes, first the circular economy actually is really key for our agriculture and forestry industry as well. And for the scalability for this hydrothermal liquefaction process, so far we already licensed the technology to some company, and they are doing the 100 kilogram per hour, the small pilot scale test. So I hope we can get some positive results from them, and then we can look at a more larger scale, so more than say 1 ton per hour or even larger. So, but in our lab we can accomplish about 6 kilogram per hour. This is
excellent.
Yeah.
That is phenomenal, you know, and you can even scale that up actually just doing some economic engineering design, but within even having an actual
technical economy analysis.
Exactly. It's wonderful work.
Thank you, Edmond, for the discussion. Thanks a lot. I guess for the interest of the time, we have 2 more questions. So one of them, Shahab, and from John, and then we can wrap up the session.
Sure.
So, and most of them are about actually corn silver, like corn stalk. So the first one is, what are the advantages of using biofoam for plant cultivation in comparison with using directly agro waste such as straw bale, which is cheaper?
Yeah, because in terms of price, definitely we can use crop residue directly. You crush them and we make some of the planting media. But those materials, the water absorption capacity is not high. You can absorb maybe 100% or several 100%. But in our bio-based foam, the polyurethane foam, as Dr. Lee present, we can absorb 1,000%. That means the 10 times of water. So this is much better in terms of water holding capacity. And also we can make the foam more air permeability, high permeability. So we can help the plant to grow.
Okay, great, good point. And the last question from Shahab, why corn stalks were used in the reactor?
Corn stalk was used here just to enhance the yield and also enhance the productivity, because the crop, the greenhouse waste, sometimes we collect it from greenhouse waste, from greenhouse. They contain too much water, say they contain 90% of water. So we want to increase the economic aspect. So we purpose to add some solid biomass from crop residue, from corn stalk, and then we can promote the economy for this process. That's the purpose. So far, we blend some corn residue into the greenhouse waste.
Okay, sounds great. And again, thank you, Charles, Lope, and also your research team for joining us and also for sharing your progress. Again, very interesting and exciting work both of you are doing. And hopefully, I guess in November, we are going to have another meetings and you can provide maybe the final outcome of your research, and we're looking forward to that event. And again, thanks a lot for joining, and also thanks to the participants for the discussion and good question they actually raised for these two presentations. Again, thanks a lot and have a good day, and hopefully see you guys in 2 weeks. We have the next webinar on May 19th, and we are going to have updates on 2 other activities from Biomass Canada Cluster. Thanks again and have a good day.
Thank you, Mahmoud,
Mahmoud,
for organizing this. We really appreciate
you very
your
much.
efforts as well.
My
Absolutely.
pleasure.
Yeah, thank you. Yeah, bye-bye.
See you.
Bye.
Bye.